All right, today we're starting our first 3 days of the unit over parametrics. Now, parametrics is not really a hard concept to understand, but in order to understand it fully, it's easiest to look at an application of parametrics. So that's what we're going to do first. We're going to look at this first, oh my gosh, this first application problem right here. Wow. Working well today. All right. So Anytown High School is planning a play. The script calls for 2 characters to meet on stage. Lauren starts at the point 0 feet, 6 feet, and travels horizontally at a rate of 1 foot per second. Alex starts at the point 4 feet, 0 feet, and travels vertically at a rate of 2 feet per second. If Alex and Lauren start walking at the same time, will they meet? So the first thing we're going to do is we're going to try to graph this. Now it says Lauren starts at 0 feet, 6 feet, and she moves horizontally, that's to the left, right, at a rate of 1 foot per second. So she's moving to the right 1 foot for each second. So we create this path along the stage, this line. That's Lauren's movement, Lauren's path. Then Alex starts at 4, 0, and he travels vertically 2 feet per second. So instead of just going up 1, I'm going to be going up 2 per each second, like so. Now, from the graph, can you determine if Alex and Lauren meet? Why or why not? Can we determine if they meet based on this graph? What do those lines represent? Shouldn't the seconds be 1 box up? Yes, it represents their path. Okay. Okay, that's okay, Grant. Okay, the lines represent their path, not necessarily where they are at a certain time period, because we're not graphing time. So, right, based on this graph, we can't tell whether or not they actually meet, because they could be at different places at different times, which they actually are. But we can't tell that from this graph. So we say, you can only determine that they cross paths. Whoops. Not whether they meet. Because time is not plotted. Okay. True, Sam, but you would need to have that prior information to know that. Like if you just took out your calculator and were to look at this graph and say, oh, do Lauren and Alex meet? You would have no idea. You would have no idea what point means what second. That's what we mean by time is not plotted. Okay, so let's try then looking at this a different way. Let's try looking at this based on tables. So Lauren is said to start at the point 0.06. She travels horizontally 1 foot per second, right? So at time 1, where should she be? If she's traveling horizontally, that's our x values. Right. We increase x by 1, and our y value stays the same. Actually, our y value will always stay the same. And our x value increases by 1 each time. So, based on this data, if I am looking at any time t, doesn't matter what t is, any time t, how does x relate to t? What will x be? This is my time, and this is my x. How does time relate to x? Yes, it'll be equal to x. Look, the time is always equal to the value of x. So, for every time t, x is also t. And what is y? What will y be equal to? 6. Always 6. Guess what, guys? We just created our parametric equations for Lauren. Lauren has a set of 2 parametric equations where x is t and y is 6. These are Lauren's parametric equations. All that a parametric equation is, all that parametric equations are, in this specific example, yes, Karina, but it won't, we're just looking at the very, very bare bones basic parametric equations we could have. So in this case, yes, but not always. So, what was I saying? Parametric equations are having an equation for both the x value and the y value while also introducing a third variable, in this case, time. One of the most famous examples or usages of parametric equations is projectile motion. So now, let's go ahead and create Alex's parametric equations. So Alex starts at 4, 0. Where is his next position? Remember, he's moving vertically, completely up from his position. So oh, you are right. Why did I think you were wrong? I don't know. I'm sorry. Yes, his x value remains the same, and he's increasing 2 feet per every 1 second. So we're increasing by 2 each time for our y value. So x will always be 4, and y will increase by 2 every time. So, our first parametric equation has x equaling what? 4. Good. What is our y parametric equation? Yes, Mia. Yeah, exactly. All we do, if you're looking at your times and you're looking at your y values, all you're doing is multiplying your time by 2 to get your y value. So our y parametric equation is y is equal to 2 times t. Yes, good job. You guys got that a lot quicker than my last classes. Okay. So now, and we're not really dealing with a calculator too much today. We are in the next couple of classes, but might as well show it to you now. If you have a graphing calculator, let me pull mine out. Okay. So here we have our graphing calculator. Let me clear this out. You need to go to mode. And if you notice on your graphing calculator, if you go to the fourth row down, your calculator will automatically be a function in function mode. For this unit, or for these first 3 days of this unit, we are dealing with parametrics. So we need to go over to that PAR. On the newer calculators, it literally like spells out the full word, parametrics, like this. And you hit enter. So now we are graphing parametrics. And when you go into y equals, it's going to look different. You're going to have x1, y1, x2, y2, x3, y3. This is because for every one what is called rectangular equation, you have two parametric equations, one for x, one for y. So I'm going to go ahead and input this example. So we have x is equal to t, y is equal to 6, x2, our second set of parametrics, has x equal 4, and y equals to 2t. So now, because we're parametrics, whenever you hit that variable button, that xt theta n, it will automatically always input t. Then we need to make sure, now it's very important in parametrics, that our window is correct. So we have 0, 6, our step is 0.1, then we have -1, 10, 1, -1. Most times, if it's going to be a hard window, they won't make you guess it on Math Excel. What they'll do is they'll give you what they want your table to look like. Let's see, where's an example of that? Ooh. Yes. Yeah, my music just randomly started playing. Okay. Oh, back to my y equals, you mean? Yes, there we go. Yes. So, right here, there we go. Here's an example of what they'll do. It'll say use the following window, and it will give you the, can I go back to window or no? Are we good? Okay. So now it'll give you the min, the max, and the step. The min, the max, and the step. The min, the max, and the step. I'm sure, I'm 100% sure that Math Excel has given this to you before. I think that Math Excel gives it like in these brackets, I believe. Not 100% sure about how it looks on Math Excel, but I think that it gives brackets. Anyway, side note, little tangent there, sorry. Wow, this is, I feel like this application is going downhill. Okay. So here we are looking at the graph of this, which looks exceedingly similar to what we graphed by ourselves by hand. What is probably more useful in this case is looking at our table. So our table will have the time values, and it will have the coordinates for both the first parametric set of equations and the second parametric set of equations. Like I said, today we're not really using the graphing calculator too much, And also, if you don't have a graphing calculator, go ahead and use that. Oh my God, I totally didn't have the chat open. I missed all of this. I'm so sorry. Oh God. Okay, hold on. Now we're just quickly going to graph 2 examples of parametric equations. We're going to create the tables and then graph them and find the start and stop time. So we know that these are parametric equations because there is both an x equation and a y equation or function, and there is a third variable t. In order to find the table values for these parametric equations, all that you have to do is input the t value. So first we're going to input 0 as our t value. 3 times 0 is 0. 3 minus 0 is 3. That's our first point. Then you repeat. We're now going to input 1. 3 times 1 is 3. 3 minus 1 is 2. And we keep inputting until we have the table filled. So 2 times 3 is 6. 3 minus 2 is 1. 3 times 3 is 9. 3 minus 3 is 0. 4 times 3 is 12. And 3 minus 4 is negative 1. Then we go ahead and plot these. And our starting point is 0, 3. Our stopping point is 12, negative 1. And we indicate, it wanted us to indicate direction. We indicate direction just somewhere on this line, putting an arrow for which way we're going. It doesn't matter where you put it, as long as there's an arrow somewhere on it. When we get to circles and ellipses, a lot of this will make more sense because you're like, okay, I don't really care where my start and stop is. But on an ellipse, if you don't put where you start and stop in direction, you have no idea which way you're going. Okay, so let's do one more. Again, it's the same process. We're taking our t values and plugging them into our parametrics to find our coordinate points. So I plug in negative 1 for t into my x parametric, and I get negative 4. Negative 1 squared is 1. 0 minus 3 is negative 3. 0 squared is 0. 1 minus 3 is negative 2. 1 squared is 1. 2 minus 3 is negative 1. 2 squared is 4. And 3 minus 3 is 0. And 3 squared is 9. So we have negative 4, 1. Negative 3, 0. Negative 2, 1. Negative 1, 4. And 0, 9. So this set of parametrics is actually in the shape of a parabola. The previous parametric was a line. We started at negative 4, 1. We stopped at 0, 9. And we put our direction somewhere on the parametric line. Any questions so far? Okay, so now we're going to be identifying or classifying parametrics. The basic shapes that we deal with parametrics are the exact same shapes that we just went over with conics. So lines, parabolas, circles, ellipses, and hyperbolas. If you don't remember how to identify or how do I look at an equation and know what type of shape it forms, Here are some nice hints. Lines have no square terms. Parabolas have one square term. Circles have two square terms with the same coefficient and same sign. Ellipses have two square terms with different coefficients and the same sign. Hyperbolas have two square terms with either the same or different coefficients, but they have different signs. So in order to practice this, first we're just going to look at these equations, and we're going to determine what type of shape they form. So, oh, my computer's dying. Hold on. Part A. What type of shape is that? Yes, that is a parabola. What about part B? So it has the same coefficient and same sign. They're both positive. It's a circle. Yes, it's a circle. Whenever they have the same coefficient and they have the same sign, it's a circle. What about part C? This is an ellipse. Yes, because we have different coefficients, but the same sign. So this is an ellipse. D? It's a line. Good. Nothing is squared, so it's linear. And lastly, E. Hyperbola, yes, because the two squared terms have different signs. One's a plus, one's a minus, making this a hyperbola. Now, like I kind of mentioned once before, like I mentioned once before, these are called rectangular equations. Because they only deal with x and y. And also, like I said before, there are always two parametric equations for every one rectangular equation. Because we have to set x equal to something and y equal to something, with us introducing a third variable. Most often time. Okay. So the reason we just went over those is because now we're going to take, I hate that this doesn't scroll. Okay, we're going to take parametric equations and we're going to identify what shape they will form on a graph. So, in order to identify what shape they're going to form, we need to convert these parametrics back into rectangular equations. And it's actually quite straightforward how we do it in these first couple of cases. All you have to do is for one of the equations, one of the parametrics, it doesn't matter which, you're going to solve for t. So normally you want to pick the easier one to solve for t. So on this number 1, which one is going to be easier to get t by itself? Yes, the x, right? Because all we have to do is add 1 to the other side. So t is equal to x plus 1. Does anyone have a guess as to what we can do from here? To make this a rectangular equation only in terms of x and y. What can we do next? Yes, exactly, yes. Wherever we see a t in the other equation, we're going to substitute x plus 1. So we have y equals 4 times x plus 1. And then we just simplify. We're going to distribute that 4 in, and we get 4x plus 4. And then we have to combine like terms, and we get 4x plus 10. So these parametric equations will create what shape on a graph? A line. That's the identification of this parametric system. Good. So let me do one more. Which one? Let's do number 4. I'm definitely going to do 5 and 6. Those are the tricky ones, but I want to do one more simpler one just so that you guys get the hang of it. I'm going to pick the easier one to solve for t. In this case, that is the y parametric. All I have to do is subtract 2 over, and t is equal to y minus 2. And then wherever I see a t in the other equation, I am going to put y minus 2. And we need to recall that anytime we're squaring, we're just multiplying that term by itself. So yes, we are going to have to double distribute here, or FOIL, whatever you want to call it. And we get y squared minus 2y plus 4. And then we just combine like terms, and we have x is equal to y squared minus 4y plus 5. So on the graph, this will form what shape? A parabola. Good. Okay. So now for the tricky 2. We know that parametrics form lines, parabolas, hyperbolas, circles, or ellipses. None of those include sine or cosine. So we know that in the end, we want this to be a rectangular equation, not in terms of sine and cosine. Exactly, Madison. Wait, are we determining the shape based on the equation we substitute the first equation into? Are we determining? You're determining the shape based on what you get when you substitute t into the other equation, or what t is equal to into the other equation. So this is a parabola. That's why we identify this parametric as a parabola. Okay, so where was I? What was I saying? We know that our equation in the end is not going to include sine or cosine at all. However, when I look at these two parametrics, do you know a way to solve for t that will get rid of sine entirely? Kind of. Close, Karina. Like, so say I was trying to get t by itself here. You divide by 4, but then to get the sine off of the t, you would have to take the inverse sine, also still introducing sine into the equation. Ah, We're on the right path. Okay. So we can't just solve for t. Instead, we have to do something tricky. And what I'm going to do is I'm just going to start solving this. And then if you think you know what I'm doing, I want you to just tell me. All right? Because I'd be interested if someone catches on. What I'm going to do first is I'm going to square. And this probably won't make sense. When I first get started, you're probably like, what the hell is she doing? It's fine. I just want to see if you know what I'm doing. I'm going to square both sides. So I get x squared is equal to 16 sine squared t. Then I'm going to get the sine squared all by itself by dividing both sides by 16. So I have x squared over 16 is equal to sine squared t. I'm going to do the exact same thing for my cosine, my y parametric. I'm going to square both sides and divide the 16 off of the cosine. Yes! Oh my God! No, you got it so quickly, Sidiksha. I am so impressed. Karina, you're so close. You're actually thinking this, what we're about to use, is a Pythagorean identity. Yes, exactly. We know that sine squared and cosine squared added together will always equal 1. They'll always equal 1. So, if I take sine squared t plus cosine squared t, I know that this will simplify down to 1. I also know that sine squared t is equivalent to, because when creating an equation, I have to make sure it's balanced. Otherwise, the equation is not logical. So, sine squared t is the equivalent to x squared over 16. And cosine squared t is equivalent to y squared over 16. And those two terms are added together. So, x squared over 16 plus y squared over 16 is equivalent to 1. What type of equation is this? It's a circle, guys. It's a circle because you have the same coefficient. Technically, the coefficients here are 1/16 and 1/16, but you could also just multiply everything by 16, and the actual equation here is x squared plus y squared equals 16. Because remember, for a circle, it doesn't have to be set equal to 1. In fact, most time it's not. It's set equal to the radius squared. So here, we identify this as a circle. So yes, this is a trig identity. We used a trig identity to help us solve this. Trig identities don't go away. Oh, because the axes are the same? Because the coefficients are the same. And they're both the same sign. That's what makes it a circle. Okay, so let me do this one more time. It's the exact same process. Whenever we're having parametric equations dealing with sine and cosine, we're going to use the exact same trig identity every time, meaning we need to create cosine squared and sine squared somehow. Now, what we're going to do first on these is we have to get the cosine and sine functions by themselves first. So I'm going to subtract 5 and divide by 7 to get my cosine t all by itself. Then I can square both sides. Oh, I'm sorry. I'm going to go over a little bit. So sorry. We talked too much in the beginning. Do the same thing for sine. I'm going to subtract 2 over and divide by 3. So sine of t is equal to y minus 2 over 3. Then I'm going to square both sides. So then I know that on one side of the equation, if I add the cosine squared plus the sine squared, this is equivalent to 1. And then on the right hand or left hand side, I'm going to put x minus 5. Now, I'm going to do 2 steps in one here. Whenever you have a fraction that is squared, you can think of it as separately squaring the numerator and denominator. So I'm just going to go ahead and square the denominator. So, what type of equation is this? Exactly. An ellipse. Because your coefficients are different, right? My coefficient on the x is 1/49 technically, and my coefficient on the y is 1/9, and the signs are the same, making this an ellipse. Are there any questions? Why did you square problem 5 before isolating cosine, but isolate cosine first in problem 6? Because of this number, these numbers. It would be a mess to try to square 5 plus 7 cosine t, because we would have to double distribute and end up with a cosine squared and a plain cosine. Like, it would just be a total mess. That's not what we're looking for. It's easy to square this because 4 sine t squared is just 16 sine squared t. If you notice, so if you look at this, and you had instead immediately divided by 4 and squared both sides, you would have ended up with the same thing. So I guess I could have just immediately immediately had square or divided the 4 off both and then squared and still ended up with x squared over 16. Any other questions? Okay. I do have a little side note for Math Excel. One of the problems asks you to go the opposite direction. So it starts with a rectangular equation like this. And then it tells you, find the parametric equations when the length of time to get around the ellipse going, what was it, clockwise is like, say, 7 minutes. So the length of time to get around an ellipse is 7 minutes. Do you guys remember what we called, when we were doing sine and cosine graphs, what did we call the length of time it took to reach all the way around, or to go through an entire one section? Yes, Natalie. Oh, I'm not explaining this well. Someone please get it. Yeah, the length of time it takes to go all the way around, or when we were doing, sine graphs, the length of time it took to complete one rotation is called the period. So if it tells you it wants it to take 7 seconds to get all the way around an ellipse, that is the period. Which, if you recall, period is always equal to 2 pi over the b value. So on Math Excel, what you're going to have to do to create these equations is you're going to have to solve for b. So here, and technically because we're going clockwise, this is actually a negative 2 pi because we're going the opposite direction than we normally would. So we'd have to solve for b here. B is actually, in this case, equal to negative 2 pi over 7. So in our equation, it would be not x, t. It would have a b value of negative 2 pi over 7. Then the subsequent y value would be sine negative 2 pi over 7. Does that make sense? What's up? Oh, I mentioned it because I said the problem tells you it's going clockwise. Oh, I don't want to overwhelm you. I know Math Excel like walks you through this problem, but I did just want to mention it. Should I just show you the problem? Okay, so it gives this rectangular equation. So this is referring to our cosine term, and this is referring to our sine term. So what we would actually have to do, like I said, if it told us 7 seconds, we'd have to solve for the period. We get b is negative 2 pi over 7. But because this cosine term, this x term, has a denominator of 25, that means that we would have a 5, the square root of 25, in front of the cosine. Also, the sine has a denominator of 16. That means that in front of the sine, we would have a 4. So that would be the true thing that we input into Math Excel. Does that make sense? X equals y equals. Okay, if not, you can go back and watch this. I think what I might do next year is like actually input this problem into these notes. I don't know why they weren't in these notes already. It would have made it easier to go over it, but. All right, so I will see you guys on Monday. You have 11.1 as homework, and I hope you have a good weekend.